Okay, let's get this next lecture underway. So I left you last time with a little problem to try and find the physical diameter of the Andromeda Nebula, given the fact that it's 3 degrees angle on the sky and 0.78 megaparsecs away. So again, this is using a formula which I hope you're now familiar and happy with using. So again, just using L equals theta d, where theta is in radians and d is the distance. So if we want to we need to convert 3 degrees into radians. I mean, you can do that several different ways if you like, but here I just, as usual, convert to arc seconds and then divide by arc seconds in a radian, and then multiply by 0.78 megaparsecs. So don't forget the units on the front. That's a common mistake by a lot of students, is to forget the kilo or the mega in front of the parsecs. And then you've got meters in a parsec here. So that gives you the physical dimension in meters. But it's much more informative to convert it back into something meaningful that we might have a scale to, so we can convert it to parsecs first. But then what I really wanted to show you is that the sort of typical units for sort of sizes of galaxies are sort of tens of kiloparsecs. Okay, so again, just to try and get the scale of things here. So typical separation between individual stars in a galaxy, or between neighboring stars in a galaxy, is about a parsec. But when you've got 10 to the 11 stars all in a galaxy, then they spread out over many tens of kiloparsecs. It's the typical dimension, like the galaxy behind me here. That would be the sort of typical diameter of a spiral galaxy. And here's again a nice little picture that's an amateur has taken in their backyard, literally, by the looks of this. So a deep exposure, just with a sort of camera lens, wide field camera lens. You can actually see our own Milky Way, which is our own galaxy, if you like, or the fact the one we're actually living in. We'll come to that in a subsequent lecture, but here you can see the Andromeda galaxy stretching out here. So again, several times bigger than the full moon itself. Okay, so as promised, today we're looking now at the material, starting to look at material between the stars. We're going to spend the next 3 lectures looking at that. It's a very important part of astrophysics, and one that's sort of dear to the hearts of many of the researchers here in the astrophysics group at the University of Leeds. So I'll introduce the idea of the interstellar medium. So we're looking at the gas today, and then go through what we call 3 different phases of the interstellar medium, the interstellar gas, so defined by its sort of physical state, if you like, whether it's ionized, atomic, or molecular. And also in this part of the module, we're really going to very much focus on sort of multi-wavelength observational aspects of modern astrophysics. So how do we go about observing the different components of galaxies? How do we probe the stars, different types of stars? How do we probe the gas content in its different physical states? And then how do we probe the dust content as well? And so hopefully as we say, by the end of this module, you'll be able to match up sort of observational wavelengths and techniques, wavebands, to particular ways of what do they actually, each of those probe. Okay, so let's define what we mean by the interstellar medium, first of all. I mean, the clue is in the name. So interstellar means between the stars, and medium means that there's something there, some kind of material. Okay, so this is the idea that space itself, so the stuff in between the stars, is not empty. There is gas there, and just like the stars themselves, it's mostly hydrogen and a bit of helium and some, and then a few % of heavy elements, but it's still got that same composition. But a different quantity that we'll get to grips with in the following lecture is the idea of what we call interstellar dust. But today we're going to concentrate on the gas. So as I say, it's very low density. So let's try and put a sort of typical number on this. So if you take, like our own galaxy, and you sort of take an average density of all the material that is between the stars, so not counting the stars themselves, and express that as a number density. So obviously you're probably more familiar with the idea of a mass density in terms of kilograms per meter cube, but this particular field very much focuses on number density, so the number of particles per unit volume. And so the average number density of the interstellar medium in a typical galaxy like ours is about 10 to the 6 particles per meter cube. So that would be mostly sort of hydrogen atoms in a typical medium. If you want to sort of visualize that, if you like, a little bit easier, so basically take 1 cubic centimeter, and you are likely to find 1 atom in each cubic centimeter if you go way out there in space in between stars. So that's a very low density. I mean, that's better than any vacuum we've ever created on the Earth. So, you might think it feels like hardly worth bothering with and that there's nothing there, but hopefully, as you'll see, then in fact, this low density interstellar medium is extremely important in the life cycle of stars and galaxies and the universe as a whole. So, as I already hinted at, then the interstellar gas, and we're kind of going to focus on the hydrogen really, obviously it's the main component, but that gas exists in a vast range of temperatures and densities. So let's start exploring that journey with in these different sort of phases. And we're going to look at a sort of fairly hot sort of phase first. Oh yeah, let me just show you another picture of this again, just another optical picture of a spiral galaxy, just to sort of illustrate what we talked about a little bit in the last lecture. So again, you've got these spiral arms here. So this time, I want to highlight these kind of red patches here. So these are not red stars, really. They're patches of glowing sort of hot gas, basically nebulae. Okay. And so as well as the sort of blue stars that you can see in the spiral arms along here, you've also got these patches of red light. And because this is an optical picture, these nebulae are showing up in the red band, and we'll explain that in a moment. So, so those red glowing patches there are basically regions of ionized gas, so ionized hydrogen, if you like. So how do we ionize gas out there in interstellar space? Well, the sort of easiest way to do it is to, if we think about ionizing hydrogen, we need to hit it with a photon that's energetic enough that it can strip the electron off the proton. Okay. And as we shall see, then this is going to happen when we are near very hot stars. Okay. So you're going to need hot stars that pump out a lot of extreme ultraviolet radiation in order to ionize hydrogen. And that is because the amount of energy you need to ionize hydrogen is this sort of, again, familiar number now perhaps, 13.6 electron volts. And if you convert that into its equivalent in wavelength, okay, so what wavelength photon do you need that corresponds to an energy of 13.6 eV? I mean, that's a calculation you can check if you want yourself. It turns out that it's here, just shy of 100 nanometers, so 91.2 nanometers, which is in the far ultraviolet part of the electromagnetic spectrum. Okay, so why do I say that? Oh yeah, let's do this first. So let's go back to our hydrogen level, energy level diagram. We saw this before when we were looking at spectral types in the Balmer series. But here we're interested in what it takes to ionize hydrogen if the electron is down in its ground state, as it normally will be in sort of cool interstellar gas. And we're focusing on this arrow here, which is labeled with ionization. So we want to take an electron that is in the ground state, the n equals 1 level here, so the lowest level it can go, and try and get it all the way out the top here, so that it's basically free and no longer bound to the proton. Okay, so it's left all of the bound quantum energy levels. Okay. And you can see the 13.6 eV label here. Okay. So that's what we're talking about if we're trying to ionize hydrogen using photons. They have to have an energy greater than 13.6 eV or a wavelength shorter than 91.2 nanometers. So again, here you can apply something you learned way back at the beginning of the course. So think about this for a second. What temperature star would you be? So what would be the effective temperature of a star that you would need in order to emit most of its photons at this wavelength corresponding to the ionization threshold of hydrogen, 91.2 nanometers. Okay, so I think what you need to make a little estimate for that question, and we'll come back and look at that after the break and its implications.